Welcome to Op-Amp Stability Basics, Part 5. After completing this course, the learner will be able to successfully use the dual feedback and 1/beta technique to stabilize an op-amp circuit, realize the effects of creating the big knot in a dual feedback loop around an op-amp circuit, understand how to use the Riso with dual feedback plus RFX topology for stabilizing capacitive loads, effectively choose a value for Riso and plot loaded AOL and 1/beta for feedback loop number 1. Apply design rules of thumb to graphically choose feedback loop number 2 for stable operation. Use the chosen feedback loop number 2 to calculate final compensation values for feedback loop number 2. Understand the loop gain test and net 1/beta on the loaded AOL curve for final rate of closure stability check. Learn how to implement a closed-loop AC transfer test for desired performance check. Effectively apply both a forward transient test and a load transient test to check for required results, and recognize how this topology fixes the DC load problem of the Riso circuit for capacitive loads. Dual feedback topologies, such as the one shown here, will have two feedback paths, and therefore two betas and conversely two 1/betas. So the question is, over frequency, which feedback path will dominate? Recall that a larger beta implies more of the op-amp output voltage, VOA, is fed back to the inverting input. As such, that means the largest beta, or smallest 1/beta, dominates over frequency to form the net 1/beta the op-amp sees as feedback. An easy analogy to remember this is that if two people are talking in your ear, one whispering and the other shouting, which one do you hear? You will hear the shouting person, which is analogous to the largest beta, or smallest 1/beta, at any given frequency. The dual feedback design guide shown here provides a simple and intuitive graphic method of plotting each 1/beta to see the expected net 1/beta. Since the dual feedback dominant feedback path over frequency rule is so important, we will review it again. The op-amp inverting input can be viewed as an ear, listening to what is happening at VOA after it passes through the two beta feedback networks. Small beta is whispering in the ear and large beta is shouting in the ear. At any given frequency, the ear will only hear the loudest beta, or smallest 1/beta. In dual feedback op-amp topologies, it is easy to plot the 1/beta for each feedback path, shown here as FB number 1 and FB number 2. You never want FB number 1 and FB number 2 to cross, as shown here, such that the net 1/beta has a pyramid shape to it. The net 1/beta, shown here as the big knot, is so named because you do not want to do this. At F_knot, 1/beta goes from plus 20 dB per decade to minus 20 dB per decade instantly. Real poles and zeros cannot accomplish this abrupt change in net 1/beta. It takes a complex conjugate pole in the net 1/beta plot, which results in a complex conjugate zero in the AOL beta plot to accomplish this change. Complex conjugate poles and zeros result in abrupt phase changes of up to plus or minus 180 degrees at the frequency F_knot. Although the rate of closure and loop gain phase margin checks at FCL will both imply stability, the criteria is invalid, since we are not using real poles and zeros. Avoid the big knot in dual feedback circuits, or you will get undesired overshoot, ringing, and marginally stable to unstable behavior. The phase plot for a complex conjugate pole pair for a few different damping factors is shown in this slide. Depending upon the damping factor zeta, the phase shift can be dramatically different than one for two real poles at the same frequency, FVP. For a real double pole, we would expect minus 90 degree shift at the frequency and a minus 90 degree per decade slope, close to a damping factor equal to 1. Here we see very rapid phase shifts at the location of the pole, especially for the damping factor equal to 0.05. The Riso with dual feedback plus RFX approach is shown here to have two feedback paths. FB number 1 is the low-frequency feedback path that ensures an accurate Vref voltage at Vout, since Vout is the point of feedback for FB number 1. FB number 2 is the high-frequency feedback path that ensures the op-amp remains stable with the capacitive load CL. FB number 2 relies on ZO or ISO and CL creating a loaded AOL that has a minus 20 dB per decade slope through 0 dB. For any practical implementation of this topology, CL is much larger than CFX, which forces the high-frequency FB number 2's 1 over beta to be approximately RFX over RF. FB number 2's 1 over beta will have a 0 in it at Fz equals 1 over 2 pi RFX TFX, and from DC to Fc a minus 20 dB per decade slope. For many designs, where FB number 1's and FB number 2's 1 over beta intersect at Fx, FB number 2 will often dominate, and there will be no correction of errors at V out through FB number 1. The design goal is to set Fx as high as possible within the limitations of making the circuit stable. First, we need to plot the loaded AOL and 1 over beta for FB number 1. We will break the loop at the op-amp's inverting input and move the CCM and CDIF externally for accurate loop gain simulations. Our ISO and CL will create a loaded AOL curve, as well as affect the FB number 1's 1 over beta curve. FP equals 1.15 Hz is the unloaded AOL low-frequency dominant pole. The loaded AOL curve shows the predicted FP1 equals 206.69 Hz due to ZO plus R ISO and CL. FC1 equals 2.27 kHz due to R ISO and CL. FB number 1's 1 over beta curve has a 0 in it at FZ2 equals 2.27 kHz. At FCL equals 13.27 kHz, we see a 40 dB per decade rate of closure, and thus predicting an unstable circuit by our rate of closure criteria. On our loaded AOL and FB number 1's 1 over beta plot, we will graphically add in FB number 2's 1 over beta curve. From our dual feedback knowledge and AOL frequency tolerance knowledge, both presented earlier, we will draw in our desired 1 over beta for FB number 2. We will adjust the high-frequency flat portion of FB number 2's 1 over beta, such that FB2, here 9 kHz, equals 0.5 FCL, here 18 kHz. Next, we will set FC3, here 4.5 kHz, equals 0.5 FX, here 9 kHz, where FB number 2 intersects FB number 1. From our dual feedback knowledge, we have avoided the big knot, and we know the net 1 over beta is what the op-amp will see for final feedback. We will also note the required gain at high frequency for FB number 2's 1 over beta, G underscore high F equals 12.4 dB. From our loaded AOL, FB number 1 and FB number 2 plot, how do we map the desired FB number 2's 1 over beta, G underscore high frequency and FC3 into circuit components around our op-amp and the required values? G underscore high frequency is set by the ratio of RFX over RF. This is because CL is much larger than CFX, so CL appears as a first-order short for all frequencies of interest. For our set value of RF equals 1 kΩ, RFX is computed to be 4.17 kiloohms to yield FB number 2's G underscore high frequency equals 12.4 dB. FC3 is set by RFX and CFX, with FC3 equals 1 over 2 pi RFX CFX. For FC3 equal to 4.5 kHz, CFX is calculated to be 8.48 nanofarads. To pad FC3 so that the zero occurs before 4.5 kHz, choose a CFX value of 9.1 nanofarads, which in turn calculates FC3 to be 4.19 kHz. The final loop gain and loaded AOL, with net 1 over beta simulation results are plotted here. Loop gain phase is measured at FCL equals 16.33 kHz to be 61.26 degrees. Net 1 over beta and loaded AOL are as we expected from our analysis. Since we used a simplified approach for FB number 2's 1 over beta, G underscore high F equals RFX over RF, instead of the actual 1 plus RFX over RF, G underscore high F from simulation is slightly higher, but not enough to not use the simplified approach. In addition, since the simulation value of G underscore high F is higher than our simplified approach, it causes FCL to occur at a lower frequency of 16.33 kHz instead of 18 kHz. Again, the simplified approach is quick and easy, and for most applications, the simulated results will be acceptable. Since compensating a circuit for stability involves reducing closed-loop bandwidth, it is important to check the final compensated circuit for application desired closed-loop bandwidth. Here we see the -3 dB bandwidth at Vout across the cap load CL is 15.60 kHz. There is no resonant peaking at VOA, the output of the op-amp, where we want to look for any stability concerns. With the type of compensation used here, there are 2 net poles and 1 zero in the final loop gain plot. The higher frequency pole and zero are known as a pole zero doublet, which will result in gain peaking out of the op-amp at VOA as shown. This is the trade-off of higher frequency correction at CL versus gain peaking. The closer the higher frequency pole and zero are together in frequency, the less the gain peaking will be. This is just expected response for a pole zero doublet. This will be covered more in an advanced class. If a wider closed-loop bandwidth is needed for the application, a wider bandwidth op-amp and/or one with a lower ZO will need to be used. If our AC closed-loop response is acceptable, we should then run a small signal forward transient test. This test uses a small square wave, 100 mV peak-to-peak on the input, with rapid rise and fall times of 1 nanosecond, to disturb the input, to look for the damped natural response out of the op-amp for a step change. At the output of the op-amp, VOA, we see no excessive overshoot or ringing, which indicates good stability. This overshoot is expected from a pole zero doublet in the loop gain. You need to look at the op-amp output and not the output at Vout in this test, since Vout could filter oscillations happening at VOA. Ensure that Vout has the desired step change response required for the given application. In addition, if the application requires certain large signal performance, large voltages can be applied and the response verified to be as needed. A good design practice is to check the op-amp datasheet for ISC and IOUT versus saturation voltage, VSAT, as the op-amp macro model may not model this behavior accurately. One final test for the Riso with dual feedback plus RFX compensation circuit is a load transient test. Many times, when an op-amp is driving a cap load, the output load transient response is critical. Here we use a stepped current source of 1 nanosecond rise and fall times to disturb the output to see the damped natural response due to a step output load. Use the application-specific anticipated worst-case current step to see the compensated circuit response. For our example, we chose a minus 10 milliamp to plus 10 milliamp current step on the output. Looking at the op-amp output VOA, we see no excessive overshoot or ringing, which indicates a stable circuit. The SPICE op-amp macro model may not accurately model the short circuit current limit at high frequency, ISC, so check that the op-amp ISC specification is not exceeded by IOUT. Look at Vout and ensure its response is acceptable for the end application performance to a load transient. A good design practice is to check the op-amp datasheet for ISC and IOUT versus saturation voltage, VSAT, as the op-amp macro model may not model this behavior accurately. The Riso with dual feedback plus RFX compensation has one advantage over the Riso compensation circuit, in that it can maintain accuracy at Vout for DC current loading. The low frequency point of feedback in the Riso with dual feedback plus RFX compensation is at Vout, to maintain accuracy under different DC current loads. As DC load current increases, the accuracy at Vout is maintained by raising the voltage at VOA due to feedback loop number 1. Here for IOUT equals 27.3066 milliamps, Vout equals 4.09599 volts for VIN equals 4.096 volts, and VOA raises to 4.28714 volts to maintain accuracy at Vout. The Riso with dual feedback plus RFX compensation is often used as an ADC reference buffer, with a large charge bucket capacitor for a transient charge supply, to maintain DC accuracy and keep the op-amp stable with a large capacitive load. Now to show a real example of the big knot when using dual feedback, we will purposely create the big knot as shown here. On the loaded AOL and net 1 over beta plot, we see the effects of the big knot in the net 1 over beta curve, with peaking at F_naught. But the rate of closure is still 20 dB per decade at FCL on our loaded AOL and net 1 over beta plot. In our loop gain plot, we see rapid phase shifts indicating a complex conjugate 0 at F_naught. But at FCL on our loop gain plot, we read 97.533 degrees of phase margin. Traditional analysis of real poles and zeros in the loop gain plot does not hold for the big knot. Here are the load transient analysis effects of the big knot. Excessive overshoot and ringing on Vout, IOUT, and VOA, voltage out of the op-amp, are seen here as undesired effects. For dual feedback circuits, avoid the big knot, as it will generally cause unacceptable performance for most applications.